Take it away, please.
All right, so I can start, I suppose. So I thank you for listening to me. I'm sorry I cannot be there, but we had some health problems in the family, actually including myself, but we're doing better now. Anyway, so this is a talk that perhaps doesn't quite fit into the majority of the talks you're listening to because it's not about causal fermions, but it's about standard quantum mechanics. And quantum mechanics still has a lot of problems, and so I want to discuss some of them. So here's a list of topics. I will first give a little review of what the problems are. Then I will look at a simple example that I think is really interesting for quantum mechanics too. That is diffusion, the theory of random walks. Then I will talk about the stochastic evolution, time evolution of individual systems in quantum mechanics. And then I will briefly sketch where this all comes from. So here is a summary to CAS quantum mechanics, incomplete in its textbook version in the final form. We must understand how to derive the stochastic dynamics of individual isolated open systems from fundamental physical principles. I show how in the non-relativistic limit with the velocity of light tending to infinity, this problem can be solved for simple systems of charged matter interacting with the quantized electromagnetic field. An important insight is that the masslessness of photons plays a key role in this endeavor. So let's start now. Quantum mechanics is afflicted by a curse. Most people who use it in their daily work appear to be unable to coherently describe its meaning. For example, to say what is meant by an event and to explain how events arise, such as the successful measurement of a physical quantity, the fluorescence of atoms, the decay of unstable nuclei, or the appearance of particle tracks in detectors. They view quantum mechanical time evolution as linear and deterministic, but go on to claim that quantum mechanics is fundamentally probabilistic, as first suggested by Einstein in 1916 and then by Born in 1926. These seemingly contradictory features of the theory have given rise to a plethora of so-called interpretations of quantum mechanics, most of which are contradictory and confusing, and also of modifications of quantum mechanics intended to explain the emergence of events. Now, I don't know of any compelling interpretation of the standard textbook quantum mechanics, and I have not learned of a satisfactory modification or extension of the theory, which is why I endeavored to propose my own attempts to do so. In textbook quantum mechanics, the time evolution of states is described by a Schrödinger von Neumann equation, or if dissipative processes are at work, by Limplach-type equations, unless a measurement intervenes, causing wave function collapse, whose probabilities are governed by Born's rule. However, measurements are quantum mechanical processes too, involving interactions between a small system of interest and a macroscopic system triggering a measurement process. So why should it not be possible to describe the evolution of the total system by a Schrödinger von Neumann or a Limplach equation? What appears to be correct is to claim that states averaged over a very large ensemble E of identically prepared physical systems, so-called ensemble states, evolve in time according to a linear deterministic law. But states of individual systems in this ensemble evolve according to a nonlinear stochastic law of dynamics. The nature of this law is the subject of ongoing controversies. It is the subject of my talk. Now, to set the stage for the ideas I want to explain, I sketched a solution to a simple problem. Let's consider a gas of non-interacting particles hopping on a lattice set nu. Nu is the dimension of the lattice and subject to thermal noise. The state of the gas at time t is described by the density rho, so T of particles. This is the analog of an ensemble state in quantum mechanics. The linear deterministic evolution equation of this ensemble state rho sub T is the diffusion equation, namely rho dot T equals diffusion constant times discrete Laplacian applied to rho T. And on the right side of equation 1, I write out the action of the discrete Laplacian. And the sum on the right side of 1 extends over all nearest neighbors sides. We would like to understand what kind of stochastic motion of an individual particle, let's call it psi, in the gas implies that the time dependence of an ensemble state rho sub T is given by the diffusion equation. The answer can be found by what we call unraveling the diffusion equation. We first have to clarify the ontology. The true state of an individual particle psi at an arbitrary time t is a site x sub psi of t in the lattice, which is its position at time t. It corresponds to a density that is given by a conical delta function localized at the position of the particle, which is a pure state. It cannot be written as a convex combination of other states. So it's pure. During a time interval from time t to time t plus dt, where dt is a small time step, a particle psi may either remain at its position at time t, or it may jump to a nearest neighbor site of its position at time t. So in this formula, y equals x sub psi of t plus delta. Delta is simply a unit vector in the lattice. The diffusion equation that we had on the previous slide, this equation 1, determines the probabilities of these different possibilities. Namely, at time t plus dt, the state x sub psi of t plus dt of the particle is given by either its position at time t with a high probability p no jump that is given by 1 minus twice the dimension of the lattice times the diffusion constant times the length of the time step, and it is given by a nearest neighbor of its position at time t with a probability that is given by diffusion constant times dt. Further jumps have small probabilities, namely higher powers of dt, and since dt will tend to 0 in the end, they can be neglected. Well, this law 2 determines what is called a Poisson jump process of the particle on the lattice. It is a discrete version of the Wiener process of Brownian motion. So law 2 for the stochastic motion of psi implies, and that's easy to see, that when taking an average over the states of all particles in the ensemble or in the gas, the time dependence of the ensemble state rho sub t is given by the diffusion equation. In other words, law 2 implies the diffusion equation for the ensemble states. Now, this law 2 has many applications. For example, it immediately determines an analog of the Wiener measure on simple random walks on the lattice parameterized by time. I give the formula you find in the middle of this slide. I don't want to go into the details of what it all means, but it's simply the lattice analog of the Wiener measure in the theory of Brownian motion. It can be used to determine lots of properties of simple random walks. You know, these properties are of great interest. I mentioned one of them. If you have two random walks in dimension 4 or more, the probability that they touch will go to 0 in the limit of large distance scales. That's of some relevance in quantum field theory. Anyway, that's how much I wanted to say about diffusion and random walks. Now let's consider an analogous problem in quantum mechanics. So, I would like to present the quantum mechanical stochastic law of dynamics of individual systems obtained by unraveling a quantum mechanical analog of the diffusion equation, namely a Lindblad type evolution equation. So we think of a very large ensemble E of systems, all identical to a specific system S, that consists of matter interacting with the quantized radiation field. In the non-relativistic limit, where the velocity of light tends to infinity, ensemble states of S are described by density matrices, I denote them by omega, that act on a separable Hilbert space H. As shown in the next section, the time evolution of an ensemble state omega sub t, t again is time, is described by a Lindblad equation, which is a linear and deterministic evolution equation. It is written in equation 3, namely the density matrix at time t plus dt, again dt is a small time step, is the density matrix at time t plus corrections of order dt plus error terms of order dt squared, which can be neglected when dt tends to 0. L of omega is a Lindbladian. And I just write the general form Lindbladians take. The fact that these time evolutions are given by Lindblad evolutions is a somewhat non-trivial statement, which I will briefly comment upon towards the end of the talk. All right, the operators V1 up to Vk that appeared in the Lindblad operator on the right-hand side are so-called jump operators. They describe dissipative effects, and these effects arise from interactions of matter with the radiation field. The constant alpha is proportional to the square of the elementary electric charge. If you turn off interactions of matter with the radiation field, for example, if you consider a neutrino, then in fact time evolution of the state would be entirely deterministic. So the dissipative effects that are important in causing stochastic behavior come from interactions with the radiation field, as I will explain in the last section. What's the ontology? As in the example of diffusion theory, we have to ask what the state of an individual system in the ensemble of such systems is. A conventional idea is that it is a pure state at all times t, namely given by a rank 1 orthogonal projection, I denote it by pi sub t on the Hilbert space of the system. If at time t all systems in E were prepared in a pure state pi sub t, the ensemble state at time t plus dt would then be given by the density matrix omega t plus dt equals pi t plus Lindbladian applied to pi t times dt plus correction terms of order dt squared. The Lindblad evolution preserves the property of density matrices to be density matrices. So we can consider spectral decomposition now of omega t plus dt. It is written in equation 4. The pi's, the pi delta sub t plus dt are the spectral projections of the density matrix omega sub t plus dt, and the coefficients are proportional to the probabilities of seeing a state that corresponds to one of these spectral projections. That's a very conventional interpretation of the meaning of density matrices. Nj stood for no jump. These spectral projections represent the possible states of an individual system at time t plus dt. It's very analogous to what I said about random walks on a lattice. The coefficients are interpreted as probabilities or frequencies in agreement with Bonn's rule, and I will explain this more precisely in the next section. Suppose now that pi sub t is a rank 1 orthogonal projection, namely a pure state, and let's assume that the time step is very small. Then we find that the first spectral projection we encountered on the right-hand side of equation 4, this pi naught, is very close to pi sub t when dt is small. Its coefficient p naught jump is given by 1 minus order dt, close to 1. It's bigger than p1, and I order these coefficients p1, p2, and so on in decreasing order. All the p deltas for delta greater or equal to 1 are order dt. The sum of the probabilities of encountering these spectral projections as states is equal to 1. That just comes from the fact that the trace of the density matrix is 1. Our task is to find explicit expressions for the probabilities that there is no drastic quantum jump, p no jump, in a time interval from time t1 to time t2, and for the probabilities that, for example, at the endpoint of a time interval, a quantum jump to a state pi delta happens with delta larger than 0, which is perpendicular to the previous state pi naught. These quantities can be completely determined with a novel tool that I call infinitesimal perturbation theory. I think it's sort of the right way of doing analytic perturbation theory. As far as I know, it is not yet in the books, but I hope it will be in the books soon. It's a very convenient tool. This tool implies the following stochastic law of dynamics for states of individual systems, whose ensemble states evolve according to the Limplad equation that I showed. Namely, p no jump, the probability that there is no drastic jump in a time interval from t1 to t2 is the exponential of a certain integral whose integrand is negative. So it's smaller than 1, as it should be, because we want to interpret it as a probability. The evolution of the state in an interval of times where there is no drastic quantum jump is given by this equation little 2, which is a third order nonlinear ordinary differential equation. It's very explicit. If you plug in the explicit expression of the Limpladian, you have an absolutely explicit expression for the evolution of pi naught. Now, we have assumed that at the endpoint t equals t2, the system exhibits a quantum jump, and the question is, what are the quantum jump probabilities? Well, they are given by the eigenvalues of a certain non-negative symmetric matrix, namely pi naught of t2 perp. That pi perp is simply 1 minus pi, then Limpladian applied to pi naught of t, and then multiplied by pi naught of t2 perp dt2. So that's a nice symmetric matrix. You can diagonalize it, and this will furnish the probabilities for finding a quantum jump in the time interval t2, t2 plus t2. It is easy to see that all these rules reduce to the ordinary Schrödinger von Neumann evolution, provided the constant alpha, namely the constant that multiplies the dissipative terms in the Limplad equation, vanishes. That's an exercise which you can try to do. So, this is a theory that determines trajectories of individual systems from a certain stochastic jump process with totally explicit jumping probabilities and evolutions of states between two quantum jumps. So it's really the quantum mechanical cousin of the Wiener process of Brownian motion that I sketched in the previous section. You can specialize this whole theory to qubits, namely two-level systems. That's particularly easy. Then you can parameterize the states of the two-level system by a vector on the Bloch sphere, and the stochastic evolution of the state is given by a certain Poisson jump passes on the Bloch sphere. You do antipodal quantum jumps. All right, now where does all this come from? You know, I think this is probably the first logically coherent theory of quantum jumps, a theory that people in quantum optics use all the time, but for which until now they only had a very heuristic foundation. So let's now give it a very clear conceptual foundation. So I would like to show why Limplad evolution appears and how the rules I sketched in the previous section can be derived from basic physical principles. So you can say dissipation in a physical system S may be caused by interactions of the degrees of freedom in S with an environment E. But already John Bell argued that we should then look at the composed system S composed with E as the total system, and that we might then argue that the states of the composed system should evolve unitarily according to a deterministic linear Schrödinger-von-Neumann equation. And you know, it's hard to argue against this point of view. However, it turns out that the radiation field, more generally any field with massless modes, represents an environment that causes fundamental dissipation, and this leads to a stochastic evolution of individual systems. And this is now something I would like to explain a little bit. So here are the basic ingredients that I will use. First, I have to define what events are in quantum theory, but at least in non-relativistic quantum theory. Potential events E in an isolated open system are described by partitions of unity, by mutually disjoint orthogonal projections of finite rank. The index set X sub E is what I call the spectrum of an event E, and it is denumerable in non-relativistic quantum theory. We will see why. At every time t, there is a representation of the projections of all potential events E of the system by concrete projections acting on a separable Hilbert space H. That's captured by this equation 6. Heisenberg time evolution. You know, Heisenberg had the right physical ideas, very much in contrast to Schrödinger. So he described the time evolution for operators and not for states, and this is how one should begin. So for all projections in a potential event E, and for arbitrary times t and t prime, the projections pi t and pi t prime that represent the abstract projection pi hat are unitarily conjugated by the propagator of the system. This allows us to introduce certain algebras of potential events. E greater or equal to t is the algebra generated by all projection operators pi t prime representing an abstract projection pi hat in a potential event E with t prime greater or equal to t. This, and then you maybe want to weakly close it so as to have a von Neumann algebra. It's immediately obvious from this definition that E greater or equal to t prime is contained in or equal to E greater or equal to t whenever time t prime is larger than t. Heisenberg time evolution implies that all the algebras E greater or equal to t for any time t in the real line are unitarily conjugated to one another. In particular, they are all isomorphic to the algebra at time 0. Here is one basic idea, and I think that sort of key idea that people have always missed during the past century until I proposed it. It's the principle of declining potentialities. In this approach to quantum mechanics, an isolated open physical system as capable of producing events, for example, of releasing photons to the outside world, is characterized by the property that E greater or equal to T prime is contained but not equal to E greater or equal to T. It's strictly smaller for all times T prime larger than T. Now we have to understand the physics underlying this principle of declining potentialities. It is an expression of fundamental dissipation. It holds in theories with massless modes, photons and gravitons, and its derivation actually depends on a certain result of Detlef Buchholz that I have used to derive it. I will briefly sketch it. In fact, it can be sketched pictorially. Consider two forward Lie cones, V plus T and V plus T prime, with T prime larger than T. Then in between these two Lie cones, there is a diamond-like region that I denote by O. Let's suppose that photons or gravitons are released from region O. They will never penetrate into the forward Lie cone V plus T prime because they speed away at the limiting speed of light. Related to this observation is the following. There is a subalgebra of operators localized in the diamond region O of asymptotic electromagnetic fields that commute with all operators localized in the forward Lie cone V plus T prime, which I denote by E greater or equal to T prime. So that's the basic result, and this can be derived from what Buchholz called Huygens principle in a relatively old paper from the 70s of the last century. Since I will look at non-relativistic quantum theory for simplicity, I should consider the limit where the velocity of light c tends to infinity. Then these Lie cones, these forward Lie cones, open up and become half spaces, and the diamond-like region O becomes a time slice between time t and time t prime. And now in the non-relativistic theory of quantum optics, the electromagnetic field, say in this pink time slice between time t and t prime, commutes with all the electromagnetic field operators at times greater or equal to t prime. And that's a very important property. Now we will see this property, this Huygens principle, is really crucial to understand quantum mechanics, and therefore I dare say that as in the genesis of relativity theory, the electromagnetic field apparently plays a crucial role in understanding quantum mechanics, which is something I think people haven't realized properly. So let's go on. What is a state of a physical system? A state omega of a system S at time t is a normalized positive linear function on the algebra E greater or equal to t. Namely, it's a mathematical device enabling us to make predictions about probabilities of potential events happening at times greater or equal to t. If the principle of declining potentialities holds, states of S at time t depend non-trivially on time t, even in the Heisenberg picture, as we will see. And this is something that people have difficulties understanding, but I will try to explain it. Given an initial state omega naught of the system S at time 0, the ensemble state omega t of the system at the later time t positive is given by restricting omega naught to the subalgebra E greater or equal to t that sits properly inside E naught, according to the principle of declining potentialities. This map does not preserve purity in general, which is a manifestation of entanglement of the system state with the states of modes that for fundamental reasons are unobservable. all of a sudden has become a little smaller. I hope you can still see it. In non-relativistic QED, when the velocity of light tends to infinity, the following special property P holds. The algebra E naught is isomorphic to the algebra BH naught of bounded operators on a separable Hilbert subspace H naught. So it's a type, what mathematicians call a type 1 algebra. Therefore, all states on E naught are given by density matrices. And since all the algebras E greater or equal to T are isomorphic to E naught, it means that all ensemble states of the system are given by density matrices. We can ask how these density matrices depend on time in the Schrödinger picture, and that is given by equation 9. The trace of omega t times a projection that represents a projection in a potential event at time 0 is said to be equal to the trace of omega naught times the projection pi of t that represents the same projection at the later time t. That defines Schrödinger evolution. The map from omega naught to omega t is linear, positivity preserving, and trace preserving. In fact, it's completely positive. And that is why the evolution that determines the time dependence of omega t is given by a Limplatt semigroup. That's a general theorem. Okay, states of individual systems. The true state of an individual system, characterized by the ingredients of my approach that I sketched so far, and by property P, typical of non-relativistic quantum theory, is given by a density matrix proportional to an orthogonal projection pi sub t in the algebra E greater or equal to t of finite rank. So let omega t plus dt be the density matrix obtained by restricting the state at time t of the system to the subalgebra E greater or equal to t plus dt that sits properly inside E greater or equal to t. Well, then this is again a density matrix. We can consider its spectral decomposition that is written at the bottom of this slide. Again, the projection pi naught is of t plus dt is very close to the state of the system pi sub t at time t. And the coefficients are ordered according to their size. Now, the spectral projections of omega sub t plus dt can be interpreted as representing a potential event, namely the spectral projection pi delta sub t plus dt for delta equals 0, 1, etc. This potential event actualizes at time t plus dt according to the following state selection postulate. And that's sort of at the core of the ontology of non-relativistic quantum theory. The true state at time t plus dt of an individual isolated system S whose state at time t is proportional to the projection pi sub t is a density matrix proportional to one of the spectral projections pi delta sub t plus dt for delta equals 0, 1, etc. The probability, the coefficient p naught is given by 1 minus order dt, and all the other coefficients are of order dt. The state selection postulate says that at each time a state is selected, in other words, an event actualizes in accordance with Bonn's rules, namely with probabilities proportional to the p deltas. The limit as dt tends to 0 is totally understood mathematically within the framework of non-relativistic quantum mechanics. In other words, in the limit where the velocity of light is taken to infinity. So these 4 ingredients that I have sketched here completely justify the procedures in section 3, and they give a solid, logically coherent basis to non-relativistic quantum mechanics. In particular, they enable us in the context of specific models to solve the infamous measurement problem and also the unitarity paradox, which people have worried about for a century, but for poor reasons. So I think all this is fairly well understood now. Of course, we would like to generalize this approach to relativistic quantum theory, and I have sketched how this might look like, but I totally honestly have to admit that the fine print of this generalization has not been worked out yet. There are many applications to quantum optics that I could have talked about, or for example, to understanding why particles trace out tracks in a detector and so on, but all this would require much more time. I have had the luck of having some nice, pleasant, good, talented collaborators that I list here, and I'm sorry, I should have replaced by Martin Zirnbauer, by Felix Finster. I gave a similar talk at the meeting in Göttingen recently, organized by Martin Zirnbauer, and forgot to change the name. I apologize. I would like to conclude by expressing my hope that people who bear responsibility in politics, bin gleich fertig, Klaus, einen kleinen Moment noch. That people who bear responsibilities in Western Europe and maybe also in the US become more reasonable again and welcome back, among other peoples, the Russian people in the European family of people. And they should try to solve conflicts by negotiations rather than by war, and work for trust and peace and the future of humankind rather than waste absurd amounts of resources for rearmament. That's my pledge, and I hope it will be heard by the younger generation of people who should really take to the streets and start to demonstrate. So, well, thanks for your attention. Of course, I'm happy to take your questions.